remain unnoticed, a fixed size hidden password file. And we want to hide the functionality or the purpose insofar as possible of the Trojan. Okay, I'm going to skip straight on to the discrimination case where we discriminate between which password we want. So in this case, we want the password of a particular user known a priori. We don't care about anyone else's password. And the critical property is that the Trojan must not reveal the user's identity while the Trojan is scrutinized at runtime. Okay, so now that's in red and it's in capital letters for a reason, so let me read it again. The Trojan must not reveal the user's identity even while the Trojan is scrutinized at runtime. This is a Trojan that goes after that user's password and no one else's, and that's our security requirement. Okay, we want a fixed size password file that's as small as possible, and we want a negligible probability of this Trojan missing the user's password if it happens to see it, receive it at the terminal when the user logs in. Is it possible to devise such a targeted password snatching Trojan and not reveal the login of the user that the Trojan is designed to steal the password of? The answer is yes, and it's extremely non-trivial, the construction for this. It's based on private information retrieval, which is a relatively new notion in crypto. It's about roughly 10 years old. I don't have time to review PIR, unfortunately, but I will go over the attack. The attack runs a query generation algorithm. He supplies it with the login of interest, and it spits out a query, which is a file. The attacker deploys this query file with the Trojan. The Trojan receives login password pairs. It runs the database administrator algorithm on these pairs as it sees them and updates the query accordingly. And this has the property that when the right login is seen, it is written to the query file, which then becomes the response file. But no other login password pair is written into this. And so this happens over time. Over time, finally it sees the user logs in. Now, one thing here is the user can't change his password. He'll actually break this system if the user changes his password. But assuming the user keeps the same password, this works. And then finally, later on, this Trojan will broadcast this query file, which is the response file, and the attacker decrypts it. And only the attacker can decrypt it because only he knows the needed private decryption key. And again, our claim is that if you analyze this Trojan throughout its entire life, every single instruction it ever executes, you will not learn the login that it's targeting. If you guys want, compile it and run it. There's the URL for this code. You'll have to, go through the process and produce your own fictitious login and password and do it. And again, these are experiments, so we encourage people to learn more about this and really just do it. Okay, here are the references. That's the one it really is very heavily based on, the Ketchin, Macaulay, Stadler paper from Eurocrypt 99. Okay, I guess do I... Oh, you want the URL. Okay. Well, I can tell you. Just go to cryptovirology.com and click on source code. But here, I'll make this bigger. It's really, this is all really quite wild stuff. Oh, I can't see. Do I have 5 minutes for questions? 10 minutes for questions? I'm supposed to stop now, right? So. Oh. Show of hands, anybody think they're going to have questions? Let me see them all at once. Hold them up. Let's do questions. I think. Okay. Yes, go ahead. It does re-encrypt, but it never decrypts while it's deployed. No, actually, Polyere is what's called an additive homomorphic public key crypto system. Okay, so the plain text range is from 0 to n minus 1, where n is the product of two large primes. And actually, what you can actually technically add any number between 0 and n minus 1 to the currently stored plain text, and it will add modulo n. Okay, but in our implementation, I believe we just do increment by 1. And so what you do is you take 0, you polyar encrypt it. And there's two algorithms you can apply to that. There's what's called probabilistic re-encryption, and then there's the increment algorithm. And you do them both. Probabilistic re-encryption is amazing. It is possible in Polyar and other crypto systems to re-encrypt a value without decrypting it. You apply this out. Anyone who knows the public key applies this algorithm. They produce a totally different encryption of all possible encryptions for that particular plain text. And it's correct in the decrypt algorithm. And the reason why that works is probabilistic encryption is a one-to-many function. There's many possible ciphertexts for a given plain text. So cryptologists will view this particular version of crypto counting as trivial. But, it's really cool applications. Does that answer your question? Yeah, I download the chapter. I think the chapter's already up. So, yeah. That's not the crypto counter idea. That's tag private information. So that's what you. Yeah, that's okay. Right, exactly. So if we go back to the slide, we're saying watching the counter doesn't count. Okay, so the idea is that obviously, if you watch the counter count, you'll know it's x plus 47. Whatever it was plus 47. You can't hide that. So yes, that's simply the probabilistic re-encryption function. You can do that ad nauseum, and you won't change the plain text at all, and it'll constantly look different. Yes. So every minute, you can do this. Every minute, you probabilistically re-encrypt. Every time they go to eBay, every minute you probabilistically re-encrypt. Every time they go to eBay, you add 1. So. All right, or whatever it is. But I think you got the idea. Yeah. Any other questions? Yes. Oh, okay. Yeah, that's well. What Modi and I basically do is we ruin the generator. Don't think of the generator. The constant G in Polyar. Okay. So G is supposed to have G is a public parameter, part of someone's public key. G is supposed to have an order that is a multiple of n. Okay. The G's that the fake key pair generate have an order that divides lambda n, where lambda is harmonized. Okay. So what that means is that you get a random nth residue every time you encrypt with a fake key, which information theoretically means you can't decipher anything. Any other? Yeah. I cannot answer that. Any other questions? Yes, Mike. You can subtract with the crypto counter. You can add and subtract modulo n. Yeah, it's modulo math. It'll wrap right back to that massive endpoint if you. Oh no! Oh boy! If you can get multiple, you get a full-fledged crypto computer. No. You get addition and subtraction modulo n. Additive. It constitutes an additive homomorphism. When you multiply two Polyar ciphertexts, you add their plaintext modulo n. It's wild. Any other? How long? 5 minutes. Okay. More questions? Yeah. I'm sorry, I didn't hear this. Writes my grants. Well. Uh, Diet Coke. Because I'm older. Okay. Used to be Coca-Cola. Another more serious question. Is that it? Yeah. You mean the traffic? Okay, that you kind of dive straight into stegonology with that. So Modi and I use lots of notions in steganography. We kind of take them for granted. Okay, so and there's a lot of very deep work going on right now in steganography. But yeah, I mean, we can make the assumption that malware is able to get a candidate photograph or video or whatever and embed stuff and hopefully be able to hide it and stuff. We view that as an API for cryptovirology. And there are other people who know far more about steganography than I do. But I think you kind of had more of a stego kind of question. Did that answer your question? Questions? That's it? Okay, thank you all very much. Yes.
Is there like a theoretical bound on how?
Oh,
Right.
very well known.
So is like algorithm the problem? Because you keep like doing it, and then at some
Your
point,
chances of it. Yeah.
we didn't come up with the
Yeah. No, right. I think that was a. Hey, that's cool. You say tomato, I say tomato.
It's getting a lot.
Oh, has it?
Remember, yeah.
Really? Yeah. Cool. When you multiply two Collier ciphertext, the corresponding plaintext add modulo. No. No, it is semantically secure against plaintext attack. I would read Collier's original paper on it. Yeah, absolutely. There have been a lot of follow-on papers to it that look